Welcome to section 3.4, solving exponential and logarithmic equations. We're going to be doing both of those today. A couple of properties we need to go back over and talk about. We got our one-to-one properties, which states that if your bases are the same exponentially or as a logarithm, then those values x of y are equal to each other. And once again, it works both ways. So if you have something equivalent, you can rewrite it exponentially or as a logarithm. And then you have your inverse properties, which I've talked a lot about, where if you have base a raised to log base a, then those cancel out and you're just left with x. Same thing with a logarithm. If you have log base a of a, those cancel out and you're just left with x. We're going to be using a lot of the inverse properties to solve these equations that we're going to be talking about. So go ahead, let's start off with exponential. So we've talked about logarithms and solving logarithms and undoing them exponentially. Well, now if we have an exponential, we can undo them using logarithms. So 4 raised to what power is going to give us 32? Well, we could kind of maybe try to figure this one out a little bit, but let me just show you kind of algebraically how we would solve this for really any type of problem. Because the base is 4, we're looking for the exponent, which means that if it's the exponent that we're solving for, a logarithm is an exponent. So if we rewrite this, we can undo this problem by using log base 4. And so I'm going to say log base 4 of 4x. And if we do a logarithm on one side with base 4, then we got to do a logarithm on the other side with base 4. And so why do I choose base 4? Well, because the exponential is in base 4. Alright, and so if I do log base 4 of 4, what happens to log base 4 of 4? It cancels. And that's what we were looking to happen. So now we have x by itself. So x is equivalent to log base 4 of 32. Well, what's log base 4 of 32? Well, we can use the change of base. We can change it to base 10 or base e. So we'll do log of 32 over log of 4. And if you plug that into your calculator, you will get x is equal to 2.5. Alright, so 4 raised to the 2.5 is equal to 32. And so that's how you can solve exponential equations now when it's the exponent that you're missing. Once again, on part B, now you might notice on part B, this one, you don't really need, and same thing for A, you don't need to use the change of base formula. You can if you want to, but this could be actually a mental math one. What raised to the power of for base 1/3 is going to excuse me, give you 9. Well, we know 3 squared gives us 9, but 1/3 squared would give us 1/9. So how do we fix that so that we make it a 9 instead of a 1/9? Well, what requires reciprocals, and that's negative exponents. So x could be equal to -2 here. So you could solve it kind of using your mental math, or we can go back and say log base 1/3 of 1/3 x is equal to log base 1/3 of 9. And the log base 1/3 of 1/3 cancels, so x is equivalent. And then once again, you can use your change of base formula to figure out what log base 9 of 1/3 is. And you can change that base to whatever you want. I actually could change it to base 3, and we could do it without the calculator because it works out nicely with base 3. 3 squared would be 9, and 3 raised to the -1 would be 1/3. So just to show you, actually, why don't I go ahead and do that? Instead of using base 10 or base e on our calculator, I'm going to use base 3. And the reason is because these both work out nicely. What's the exponent? 3 raised to what power gives you 9? 2. And 3 raised to what power gives you 1/3? -1. So x is equal to -2. Or you could have used base 10. That's fine as well. Part C. Now this one, if you pay attention, the unknown is no longer your exponent. So do we really need to write it as a logarithm if we're not looking for the exponent? And the answer is really, well, no, because that's not going to help us solve. This is x to the 0.25, which is 1/4. And if we have x raised to the 1/4, I'm going to erase this in just a second, but that's saying that that is the 4th root of x. Well, how do you undo the 4th root of x? You raise it to the 4th power. Now I'm going to get rid of that, because the same thing happens even when you have a rational exponent. If it's x to the 1/4, if you just raise that to the 4th power, 1/4 times 4 is 1. So it's x equals 12.3 raised to the 4th power plug that in your calculator and you get 22,888, and it does terminate, so I'm going to write all the values down. 0.6641. And so that's the value that you get for x in terms of the base. So there's a couple of examples of exponentials. We'll continue to work on a couple more here, but that's the general idea of how this works. On the next one, we got 3.9 raised to the x plus 1 is equal to 28. So we've added a couple more things in terms of the exponential. It's not just x, it's x plus 1. But that doesn't change how we're going to solve this. If the base is 3.9, then we're going to rewrite this as log base 3.9 of 3.9. And then on the other side, you get log base 3.9 of 28. And so why do we do this? Same thing from before. Because we want this to cancel. We're using inverses so we can get the exponent by itself, which is x plus 1. Now over here, it doesn't cancel, but we can use the change of base. So we'll just do base 10, log of 28, divided by log of 3.9. So that will give us an answer. And then what we'll end up doing is subtracting 1. So before I plug in the calculator, I'm just going to write the whole thing out. Log of 28 divided by log of 3.9, and then we're going to take that value and subtract 1. Okay, so then you'll plug this into the calculator and see what we get here. So we got log of 28 divided by log of 3.9, and then we can take that value and subtract 1. So we get 1.448. We're going to be rounded to the nearest thousandth place. Alright, what happens if we do natural log? I showed you this as well the other day. It doesn't matter what base we choose. So if I do natural log of 28 divided by natural log of 3.9, we're just using base e now, but by the change of base formula, it doesn't matter what base you change it to. So we still get 1.448 approximately. So x is approximately 1.448. And that's another way in terms of solving exponentials using those inverses. On the second one, you can try this one on your own if you'd like. We need to isolate. You always have to isolate the exponential part of it. You got to get the base and the exponent by itself. So we have to do a little bit of work here before we use logarithms. We're going to add 4. That'll give us 15. 2 times that, 3 raised to the 2t minus 5. We then need to divide it by 2. So now we have 3 raised to the 2t minus 5 is equal to 15 halves, or 7.5. And then now once again you can use logarithms. So I can say log base 3 of 3 and log base 3 of 7.5. So you'll see it again. Cancels. 2t minus 1, that was the inverse. And then on this one we can use the change of base again. Log of 7.5 divided by log of 3. Now plug that into our calculator, get a value. So I'm going to continue to simplify before I plug in. So I would add 5 to both sides. So 2t is equal to now log of 7.5 divided by log of 3. And then I had to add 5. And then my last step is to take all of that and divide by 2. And then I'll plug in. What I don't want you to do is take log of 7.5 and divide by log of 3. And approximate that value and then approximate as you go along. You want one answer at the very end approximated. So I'm going to keep this answer in my calculator, and then I'm going to now add 5, which is what I was supposed to do next. Keep that answer in my calculator and then divide by that final quantity of 2. And so here's my answer to the nearest thousandth place, the most accurate that I can get, 3.417. And there's your answer there. And so there you have it in terms of solving exponential problems. We'll continue to work on a couple more exponentials and then move on to logarithms. But when we move on to our next exponential, I've changed the base a little bit. We're going to look at the base of e, which is the inverse of the natural log. So when you're looking at these, you still are solving for the exponent. So we do want to use logarithms. But when we go to do a logarithm, we want to use the base that the exponential is, and it's base e. Now, if I put log base e, that's fine. I don't have a problem with you putting log base e, but you need to understand that log base e is the natural log. So this is really natural log of e raised to the x and natural log of 7. So natural log of e raised to the x, that cancels and just leaves you with x, because the base is base e, just like you can see up here. That cancels. Alright, so a natural log is log base e. E raised to the x cancels, and you're left with natural log of 7. If you plug in the natural log of 7 into your calculator, natural log of 7, that's it, 1.946. And there you go. And so same thing on part B. Go ahead and pause and try to work this one out yourself. We do need to isolate the e, the base, before we can do the natural log, just like always. So we have e raised to the 2x is equal to 5 divided by 4. And then now we can use the natural log of e raised to the 2x and the natural log of 5/4, or 1.25. And so that cancels, and it leaves you with 2x equals natural log of 1.25. And then divide all of that by 2. So natural log of 1.25 divided by 2, plug it in your calculator, and you get 0.112. So that's how you solve exponential equations, is by using the inverse, which is logarithms. So let's kind of move on now to the logarithm side. We already solved some logarithmic equations before, but we're going to look at a couple more today. This is the natural log of x is equal to -3. How do I solve this? Well, if it's written as a logarithm, we want to undo it by using exponentials. Well, this is natural log, so what am I supposed to do here? Well, remember, and once again, I don't mind if you write this, natural log is log base e of x. So how do you undo that? Well, the base is e, so I'm going to say e raised to the natural log and e raised to the -3. And when you do that, you can see that they're inverses of each other. They cancel, and so you're left with x is equal to e raised to the -3. And then you plug that into your calculator. So what's e raised to the -3? E is the inverse of natural log. So you have to press second natural log, and then you'll plug in the -3, and you get 0.049 and then the 7. So you do have to round up the 49 to 50, or 0.050. So 0.050. And there you go. So same thing as previously, but we will be using calculators on some of these questions, whereas before we were doing everything without one. And so here, let's practice a couple more. I just got a couple more examples to kind of go through with you guys on this. If you want to pause it and work through some of these on your own to see if you know how to do it, I think it's a great idea. Number 4, log base 10 of x. It doesn't say 10, but you need to understand when the base is not written, that's the common logarithm, so it's base 10. So we say 10 raised to log 10 and 10 raised to the -1. That cancels. You're left with x equals 10 to the -1, which is 1 over 10, or 0.01. 0.1. On B, we have log base 3 of 5x minus 1 equals 4. Same thing. 3 raised to that, because it's a single logarithm, so it cancels. 5x minus 1 is 3 to the 4th, which is 81. Add the 1. Divide by the 5. And you get x is equal to 16.4. Alright? So both of these logarithms, you didn't necessarily even need a calculator for these two. So similar to what we have done before. Same thing on C. Now on C, we can't put the 5 here just yet to get this to cancel because we have this 2 here. So what do we have to do with the 2? Well, we've got a couple options on this one actually. A lot of times we're going to go ahead and move it to the exponent and deal with it that way. Now that will create a quadratic, so it might create some extra solutions that actually are not solutions. Or because on this one it's equal to a number over here, if this was equal to a logarithm it wouldn't work, but since it's equal to a number, if we divide everything by 2, the 2 cancels and you're left with log base 5 of 3x is equal to 4 divided by 2, which is 2. Now go ahead and do 5 raised to log 5 and 5 raised to the second. That cancels. 3x is equal to 5 squared is 25. Divide by 3. X is equal to 25 thirds. And there you go. So more logarithm stuff. I'm going to give you 4 more examples. Once again, I really suggest you go ahead and pausing and working through these 4 problems on your own and seeing how you do on each of these. Log base 8 of 92 is equal to x. We do know the change of base formula now, so we can actually use the change of base formula to solve this. If you get confused and you say, oh, I'm going to use the inverse. I'm going to say 8 raised to that, and that cancels here. Well, now you're looking at 92 is 8 raised to the x power. Well, you don't know the exponent. That's why it's written as a logarithm in the first place. So understanding the type of problem is going to help you guys solve each of these. So this one's already solved for. You already have x by itself. You got to figure out what log base 8 of 92 is. And that's using your change of base formula. So on this one, let's use natural log. So we'll do natural log of 92 over natural log of 8. No, it doesn't matter which one you use. Just want to show you different options here. So x, when you plug that in, we'll do natural log of 92 divided by natural log of 8, and we'll get 2.745. So 2.175 is what we'll use. 2.175. All right, on B. B's an interesting one. You can kind of do it a couple different ways. I'll do it actually both ways so you can see it. So the first way is, okay, we're subtracting, so we're going to use division. That would be the natural log of x over 3 is equal to 0. It is natural log, so we can say e raised to both of those. That will cancel, leave you with x over 3. E to the 0, anything to the 0 is 1. And then you can multiply by 3 and get x equals 3. So that's one way to do it. The other way, because this is actually equal to 0 over here, you might have realized that you can actually add the natural log of 3 to the other side. And now you have natural log equal to a natural log. So to show you the math, the inverse, if you take e and raise it to both sides, you're left with x equals 3. So either way will work for something like that. On C, you have a natural log, but you need to do a little bit of work to get it set up so that you can do the inverse. So we need to subtract 5. We're left with 2 natural log of x minus 2 is equal to negative 1. We still have this 2 out front. We have to do something with it before we do the inverse. So what is it that we want to do? Well, we could move it. It would create a quadratic. So instead, because it's equal to a number, I'd rather just divide it by 2, even though it'll create a fraction. That's alright. That's negative 1/2. And then now rewrite it in terms of our exponential using the inverse. So e raised to the natural log, e raised to the negative 1/2. Cancels, leaves you with x minus 2, and then whatever e to the negative 1/2 is, we'll add 2 to both sides, and then that will give you your x value. So we'll do e to the negative 1/2, e to the negative 1/2, and then we needed to add 2 to that when we were done, so we get 2.6065 or 2.607. And there you go. Alright, and on the last one, once again, natural logs, but same properties as logarithms. You are adding 2 natural logs together. There's no numbers in front on the bottom, the second 2, but there is on the first one, so we are going to have to move this and do the natural log of x squared is equal to the natural log And now these two things are being multiplied. X minus 2 times 2x minus 3. So we have natural log of x squared is equal natural log of 2x squared. It'd be negative 3x and negative 4x, so that's negative 7x plus 6. And since it's a natural log equal to a natural log, we could take e raised to both sides, and that will leave us with those cancel, so you have x squared equal to 2x squared minus 7x plus 6. Looks like we got a quadratic, so I'm going to subtract the x squared to both sides. And that will leave us with x squared minus 7x plus 6 equals 0. Solve both of those and get x equals 6 and x equals 1. Now, one of the things I get to the end of the notes and just realize that, really I should have been checking these values when I, to plug them back in. For example, going back up to b. X is equal to 3. Well, when I plug it back in, does it give me a positive number, something greater than 0? Yes. 2.607. If I plug it back in for this x, does that value greater than 0? Yes. So I really needed to be careful as to when I was doing these logarithms that the answers that I was getting give me values that were greater than 0. Well, on this one, I got two solutions. And so when I go to plug these back in to these values up here, do they both work? For example, taking x equals 6. If I plug it in here, 6 is greater than 0. If I plug it in here, 6 minus 2 is 4. That's greater than 0. And if I plug it in there, I get 12 minus 3, which is greater than 0. So x equals 6 is a solution. Now, when I turn around and plug 1 in, what happens? Well, if x is 1, greater than 0. If x is 1 here, we get 1 minus 2, which is negative 1. That is not greater than 0. And the same thing happens here, not that it matters, but you get a value that's less than 0. So, at that point, x equals 1 does not work, and your only solution for this logarithm equation is x equals 6. And so that finishes up solving all the logarithmic equations and exponential equations. A lot there. Make sure you guys do your homework on this and practice all these different types of equations.